All right, good morning or evening or afternoon, whatever. Depends when you watch this. We're going to talk about the second half of 20-1's trigonometry unit, which is all about two rules, two laws that let us work with oblique triangles. Now, remember our trig ratios from 10C and what we looked at a little bit in the last lesson here are only for right angle triangles, and oblique are triangles that don't have right angles. So you can't quite use the same ratios, or at least not in the same way. So here's an example below where we'll try and find out what a missing set of measurements are for a triangle. Now, we've got a couple ways that we can do this, but I'm going to just start off by looking for this side right here. And I realized in the last video that when I hover my mouse, you can't see it at all. So I did a lot of that, but this time I'm going to try and be a little more helpful. And in order to find that, what I'm going to do is I'm going to use the ideas that we had from before with right angle trigonometry by making a right angle. So I'm going to break this triangle down into two pieces. And by doing that, I've created two right angle triangles. Yes, that's an excellent right angle symbol. And this line that I've created, I'm going to call it H. And it's going to be something that I can find by using the sine ratio, right? I've got an angle and I've got the hypotenuse, and I'm looking for opposite over here, or in this new triangle I've created. And then I can then use the sine ratio on the other side because I've got the angle. I can find the hypotenuse once I've found this opposite side. And I'm actually, for this video, only going to kind of demonstrate this one side because I could essentially be doing the exact same things for breaking it another way to find this missing measurement. And this angle is actually really easy. Just remember our interior angles of any triangle are 180. So I know that it's an 80-degree angle. So kind of one of the things I'm missing is easy, and the other two are sort of the same trick. So let me show you the trick. All right, so in order to find H, we're going to use, like I said, the sine ratio. So I really like writing out, sorry, that probably was really noisy. My formula first, O over H. Since I'm not using a Cartesian plane, I'm going to use O and H instead of Y and R. And then I'm going to rearrange to find for my opposite, which in this case is H. So H is going to be equal to, I was already in pen mode, sine of my angle, 40 degrees, and that's going to be multiplying by 5. So I'm going to whip out my calculator and do that for any lesson where I'm doing trigonometry, especially when you are, I guess, also teaching 30 at points. Always make sure your calculator is in the right mode. Mine is. So I get this. H is equal to 3 round to the nearest tenth. Let's go 3.2. But I'm going to keep this number as the bigger approximation in my calculator when I apply it in the next step. Okay, so for my next step, sorry, there's something on my screen. For my next step, I'm going to use H in order to find this. So I'm going to rearrange this formula again now to find my missing measurement. In order to find the hypotenuse, it's going to be our measurement here, H. And let's actually give this a label. Let's call this X, just so I can write this. So X is going to be equal to H divided by sine 60. And if you're kind of like, well, where did that formula come from? Spend a minute, just review your trig ratios and how you can reorganize them algebraically, and that'll help you out. Okay, so I'm just taking H and dividing it by sine 60. So that is that divided by sine 60. And that will give me a value that X is equal to 3.7, rounding to the nearest tenth. So this is my value for X. Again, I could do the same trick, just divide this into two right angle triangles. Let's do a purple line here, kind of like this, if I wanted to find what this missing side is. Because now I have this, I know this angle, I know this angle. I can do the exact same trick. So it's not that exciting. You just piece. And so that idea of breaking into separate right angle triangles is actually really nice because it lets us use our trig ratios still. And those trig ratios will always work out for us as long as we've made right angle triangles. But it's pretty onerous, especially like I said, I'm only doing it once because I don't want to do it twice. I've shown you the trick, but it takes a lot of time. Wouldn't it be nice if there was a simpler way to do that? And in fact, there is, and it's called the sine law. So if we go to the next page, this line from B to D, which often is called our height, there's kind of two ways that we can find it. We can relate it. The first way over here is by saying that, for example, this is in line mode. Let's try this. Sine of A is equal to this line BD. I'm going to just call it H just to make our lives easier. H divided by little c. And over here on this side, we can also say that sine of angle C is equal to H divided by A. Little a over here, this little a, this little c, right, just from our diagram. And since I have this same measurement H in both of my equations, what I'm going to do is I'm going to show, when I rearrange them, that they can be equal to each other. So if I multiply both sides by c in my left equation, I get sine A times c. And if I multiply both sides by a in my right equation, I get sine c times a. And the last step is to, well, actually, like this is really helpful, but the last thing most times people will do is they'll actually divide, now that we know these are equal to each other, divide our side lengths over to the other side so that we get this match. And that's our sine law. Sine of angle A divided by A will have the same ratio as sine of angle B divided by B, sine of angle C divided by C. So all these ratios are going to be the same. One thing to kind of remind yourself is that when we label triangles, angle A is always opposite of side A. So our angle side naming schema is always just the angle, big letter, has a matching side across from it. And so the ratio of sine of an angle and the side across from it is equal in any oblique triangle. And since it's a ratio, we can also do like the reciprocal version of this. So if I have a ratio and I do the reciprocal, then any ratio that was equivalent, the reciprocal of those equivalent ratios will also be equivalent. So we have two ways that we can write this. We can have the angles on top, or we can have the sides on top. And just remember our letters match. You will have a formula sheet anytime you're doing a trig test with me and most teachers, but it's not a very hard one to memorize as well. So that's nice. Why would we even write it two ways? Well, when I think about algebraically rearranging my trigonometric ratios, it's kind of a pain in the butt when I have to do a lot of flipping and flopping of everything. And so having it where you can either put the angle on top or the side on top is nice, so that when you're solving for angles, you can use the one where all you have to do is multiply A over from the bottom. And if you're solving for sides, then use the one where our sides are on top, so you just have to multiply the angle over. That's really easy. All right, so that's our sine law. The sine law requires you to have a specific amount of information. You need to have three pieces. And sometimes they'll be like given to you. Sometimes you'll have to do a little bit of digging, and I'll show you both situations. So the three pieces is a matching pair. And what I mean by this is you need to have, for example, like big A, the angle, and the side across from it. So in order to use like an equivalent ratio, you actually have to have the full ratio that you're comparing with. So you need to have a matching side, and then you need to have one, nice letters, other piece. And this might become more clear when we do some examples here. But the critical thing is you have to somehow make this matching set so that you can set up a equivalent ratio. So here's an example where we're looking for a side. And when I say like a matching set, here is an angle and its opposite side. This is a matching set, right? We have this full group. And because of that, we're able to use the sine law, which is really nice. So I'm going to go ahead and I'm going to set up my formula, and I'm just going to write it like this. I got sine. No, I'm finding a side. So let's use A over sine A is equal to B, little b, over sine B. Okay. And so I'm going to call this B and little b, A and little a. And I don't necessarily have to do that labeling, but just for this example, I'll show you that. So if I want to isolate for A is this variable we're looking for, L. In order to isolate it, what I'm going to do is I'm going to multiply both sides by sine A times sine A. So that over here, that's divided out. And I get this B, which is 15 centimeters, times sine A, which is sine 35 degrees, divided by, where's our last bit? Sine B, which is 110 degrees. So when I type this in, just one thing to be wary of on your calculator, and I'm not going to show you how to type it on your calculator. Hopefully you can figure that one out. If you need to, look up another video with the actual commands on it. Just careful with your brackets, because if you have sine 35 on top and you leave the bracket open, you're not going to be doing sine of 35. You're going to do sine of 35 divided by sine 110, which is a totally different number. So just make sure you're careful closing your brackets. Since there's only one thing in our denominator, you don't need to be too squarely about how many brackets you put in the denominator. And that gives us an answer, and that tells us that L is equal to 9.1. It doesn't say how many decimals, so let's go 9.16, and that is centimeters. Okay. Now, one thing I'll caution you on this is that I'm pretty sure this scale is off. Like, this is not 35 degrees. It looks closer to 45. Not a big deal. You should always double check, though, even if the triangle looks a little wonky, that logic of, does your answer make sense? So remember how I said a larger camera takes a larger picture. So if you have a big angle, the side across from it is going to be bigger than if you have a small angle. So once we've done our work, we should double check, does the answer 9.16 centimeters make sense? Well, in order for it to make sense, it has to be less than 15 centimeters. It is less than 15 centimeters. That's a good sign. And I don't look and say, like, well, how much less should it be? It should be only 1/4 or 1/3 because that's roughly the ratio of the angles. No, that's wrong. It's not a linear relationship between angle size and opposite side length. And I'm not going to compare it necessarily to the picture either, because again, your picture might be made by me and I suck at it and it won't be to scale. So trust the logic, but don't try and overcomplicate that logic. All right, so that's an example where we're finding a side. Let's do an example where we're finding an angle. So with this, again, I have that matching set. I have 65 degrees and 17 centimeters. Those are matching across from each other. And this one, I'm not going to label it quite the same way. I'm just going to kind of go through it how I would do it in like a normal question while still showing all of my works. So I'm going to write it in that form. We've got sine A over A is equal to sine big B over B, which means that theta is going to be equal to sine of 65. Well, actually, let's leave it as a sine theta. I'll do it in 2 steps. Sine theta is equal to sine 65. Remembering my brackets, I'll write that out just to help you guys remember that. Times, well, we multiplied A over, so that's times 10 centimeters divided by little b, which is 17 centimeters. All right, so I'm going to do this, like I said, in multiple steps just to kind of walk you through an idea here. So sine 65 times 10 divided by 17 gives us approximately 0.533. There's no units to this because centimeters cancel out, but I'm not super worried about your units. This value, before we kind of isolate for theta, has to be between 0 and 1. It'll never, ever be above 1. If it's above 1, that means it's impossible. You cannot have a ratio where your hypotenuse is greater than your opposite. That doesn't happen. It's not possible for triangles. And so in some cases, you will potentially run into things where it, just by plugging it in, it won't work. The information that's given to you then means that the shape's impossible. You cannot have a triangle with those characteristics. An example of this is my old version of the notes where I accidentally just put random numbers in to try and do this more quickly, and it made a triangle that couldn't exist, and I felt dumb. Okay, let's find out what theta is. In order to do that, what we're going to do is the inverse operation of sine, and that is arc sine. So that's second function sine on your calculator. And I apply that to both sides such that I get, drum roll please, about 32.2 degrees. Okay, let's double check to see if our answer makes sense. Larger side across from 65 degrees means that the angle across from 10 degrees has to be less than 65 degrees. So yeah, 32, that works. And again, I don't care that it's proportional, blah, blah, blah. I just know it has to be less. Great. Hey, do some practice. It's really good for you. Yeah, look at that. Look at that. Woohoo. Practice, practice, practice. Okay. Now, one thing that's really important with the sine law is related to what we learned in the last section, and that's our cast rule. So if you remember our Cartesian plane here, we've got cast, which means that when I'm doing this work, our cosine ratio is positive in quadrant 4. Everything's positive in quadrant 1. Sine is positive in quadrant 2. And tangent is positive in quadrant 3. This leads us with a bit of a nasty scenario when we're doing the sine law. And that's that when we calculate for an angle, we're going to get a value that is popped out as a reference angle. And so what does that mean? Well, that means it could be giving us the reference angle in quadrant 1 that matches the standard position angle, or like the actual angle of the triangle. Or it could be giving us an angle from quadrant 2, because a positive sine reference angle could be just a large standard position angle. Ooh. And we know that a triangle has an interior sum of its angles being 180. So it's possible to have one of these larger angles in it. So this is called the ambiguous sine law. And that means your answer is telling you either the reference angle from quadrant 1, which means it's that angle, or it's giving you a reference angle from quadrant 2, which means it's actually a bigger angle. Let's do an example to see that. Here's some information that's given to us. And the other thing, I guess it might be implicit, but might not be super obvious. The ambiguous sine case isn't something you need to worry about when they draw you a triangle. When they draw you a triangle, you'll see, oh, the angle I'm looking for is like this, or the angle I'm looking for is like this, right? And in that case, this is small. It's not ambiguous. You know it's less than 180. This is big, less than 90. This is big. You know it's more than more than 90. So there's no ambiguity when you actually see it drawn there. But let's take a look at this. All right. To fulfill these characteristics, we're not going to use a ruler or protractor for this task. I'm going to just go ahead and draw this out for you once we've done the work. So they give us angle A and side A, so they kind of give us one match, but we don't know what angle B is. So let's go ahead and let's write out our sine ratio to find out what angle B could be. And then we'll go ahead and we'll draw that version, and then I'll show you another form that's possible. Okay, so for B, it's going to be arc sine of B times sine A over A, just doing the algebra there really quick. And so I'm going to go ahead and type that in on my calculator here. That is going to be 16 times sine of 30 divided by 10, and I get an angle of 53 degrees. Okay, so this is a possible angle wherein I've got roughly a 30 degree, right? So that we'll call this A, and then you've got about let's see what we want to do here. 50 degree, right? And this is B. And then C, thereby, is actually going to be, this is not quite perfect. Here, let me draw it again. Let's go. A is up like this. B is about a 50 degree. It's like roughly that. And, oops, that's still not quite right. 50 degree, more like that. And so C is something like this. Okay, so when I have this situation where B is a little bit smaller, we'll call that about 50 degrees. That's one version of this triangle. But if I think about like my cast law, which I'll put in the middle here, with the cast law, it's saying, yeah, your standard position angle could be 53 degrees like this, right? Or it could be, because it's positive in quadrant 2, a reference angle of 53 degrees, which means our line is actually like this. And our reference angle matches then with a standard position angle of 180 minus 53, or 127 degrees. So it's possible that instead of being like this, we actually have A, which is about 30 degrees, and then B, instead of being a tighter angle, is actually a big fat angle like this, which is 120 degrees. Okay, so we actually have two triangles where we could have the sides matching out properly, but we would have different measurements. And this is kind of a bit creepy. And obviously, like you might say, well, this and this, both being B, those are not the same lengths. That's because I suck at drawing. I recommend, if you're really curious, why not you go ahead and you actually draw this with rulers and protractors and see what you can do. And you'll find that both of these triangles are possible. You can have a triangle where B is 53 degrees, or a triangle where B is equal to 127 degrees. Both of those triangles are possible. So how do I test to know if both these triangles are possible? Well, the answer it gives you is always possible. Okay, so the smaller angle is always possible. The larger angle you check by seeing if it follows the rules of every triangle. If I already know that A is 30 degrees, I need to make sure that I can fit an angle of 127 degrees in this triangle and still have some left over here. So here's a rule. If A plus B is less than 180 degrees, then both triangles are possible. And that's essentially saying I just need to have some room left, some angle left, in order to have an angle C, right? Triangle, there has to be enough angle for three angles. So in this case, 30 plus 127 is 157, so there's tons of angle left. That means both triangles are possible. Again, I recommend grab a piece of paper, grab a protractor. If you're doing this at home, I'm sure you have a protractor lying around because you're a big dork. Some notes down below. Not going to do this problem example. Try it out. Now, that's the first of our rules. The second rule comes from when you would like to do the sine law, but you just don't quite have the right information. So we said that we need like a match of two pieces that go together, so an angle and its opposite side. So this one I can do sine law perfectly. Whoa, nice W. There's a new W. Okay, sine law works over here if I have that match. And so often what you'll get is something that has like angle, side, where our angles will match with one of the given sides. And even if it didn't, so even let's say they give us this instead, I can find this missing angle by just taking 180 minus the others, and then I have a match. So angle, side, if they give you two angles in your oblique triangle, you can always use the sine law. However, sometimes you're not given that. So you're going to get instances where I got side, side, and in side, I don't have any match. Like I don't have this or this or this. So I don't have enough information to use the sine law. So no signing. Okay, it's like you're at a convent. No sin. Anyways, so the sine law doesn't work if you get all the sides. There's also cases where, oops, I double 40 forward there. You have angle side side where you just don't have this match, right? Sometimes we have a match. So if they give us this angle and two sides, it would work. If they give us this angle and two sides, it would work. So unfortunately, this one, angle side side, it doesn't work, right? Yeah, there's a joke here somewhere. So no sine on this one. Okay. So what are we going to do? Well, we're going to use something called the cosine law. For this video, I'm not going to show you a proof of the cosine law because you're not required to memorize it. But essentially, we did the same game plan that we did last time, where we are using breaking it into two triangles and relating both of our triangles to this distance h. But we actually use a slightly different approach, which includes the Pythagorean theorem. Yeah, like I said, I'm not going to show you this because the math is a little onerous and you don't need to memorize it, but it's interesting to look up. There are a lot of videos that you can watch on that. It gives us this rule in the end. Sometimes the letters are a little different, like your A's and B's and C's might be in different spots, but here's the key thing about it. C, the side length, matches with C, the angle. There's only ever one angle, and so what you're focusing on is in a triangle, you've got this matching set where you know one of them. For example, in this case, you know the angle and you're trying to find the side. Or we can actually rearrange this and we can find the angle if we know the side. I think later on in the notes, I have how to find or rearrange the formula to find the angle C. So we'll look at that then. But for right now, let's do an example where we're using the cosine law to find a missing side. So in this case, I'm going to just copy down my formula. I get c squared is equal to a squared plus b squared minus 2ab cosine c. Remember that you have a formula sheet. This is going to be on it. You don't need to memorize it, but it's a really cool party trick if you do. Okay, I'm going to isolate c by square rooting both sides, and I'm going to start plugging my numbers in. Notice that A and B are kind of symmetrical in where they appear in the formula. It doesn't matter which one you call A and which one you call B. Just make sure C, is this matching set. C. It's the angle and side that we're trying to find one of them, okay? So I'm going to call this 14 squared plus 16 squared minus 2 times 14 times 16 times cosine of 80, okay? So that's my formula. Now you guys get to twiddle your thumbs and wait while I type that in on my calculator. Most of this is pretty safe for calculator typing. You don't have to worry too much about your brackets, but I would often do this. Just put a big set of brackets around there just for peace of mind, so I don't have to worry about, did I screw this up? Did I screw that up? It just keeps life easier. Okay, once I've done that, it doesn't say what rounding I should do, so I'm going to just go to the nearest tenth. I get 19.3 centimeters. Just like in the sine law, I'm going to go ahead and make sure that my answer makes sense. If this is an 80-degree angle, it's very difficult for both of these to be larger. And just looking at the picture, it doesn't look like they're larger. So I expect that the side that's opposite of 80 degrees is probably the largest. 19.3 centimeters is larger than either of the other sides, and so yeah, that makes sense. Okay, so like I said, we also want to find out our missing angles sometimes, so here's how we rearrange that formula. And I've seen this done more than one way, like so that it's left in a different form, and it's not as good in some other ways. So you really kind of want to make sure that you do something that leaves you a nice answer. So if you look at another video and it gives you another way and you're like, wow, that looks like a worse formula, don't use that way. The one I'm going to show you here is as you see on your formula sheet. Only difference is that you might have like A's instead of C's, like the A's and C's might switch spots. Again, the only thing that matters is that C matches with C, or that letter matches with that letter. All right, so I'm going to show you kind of maybe that European style here. What I'm going to do to start is I'm going to add 2AB cosine C. Remember, this is just saying this is the steps I'm doing. So when I do that, I get C squared plus 2AB cosine C is equal to A squared plus B squared, right? Because it adds from one side to the other. Then I'm going to subtract C squared from both sides. And so that gives me 2ab cosine c is equal to a squared plus b squared minus c squared. And then I need to isolate kind of for my angle. So I'm going to get rid of this coefficient. I'm going to divide both sides by 2ab. And that gives me what you'll usually see on your formula sheet. Cosine c is equal to a squared plus b squared minus c squared divided by 2ab. And then, of course, if you really want to isolate c, all you have to do is arc cosine. All right, so that's second function cosine, cosine -1. That's what the button used. So this is arc cosine that we're applying to both sides. And that would give me this. Angle C is equal to arc cosine of all that junk inside the brackets. What do you think? Okay, this is a B, not a 6. Forgive me. So that's our other form of our cosine law. This one's got a lot more going on. And so when you are writing it in on your calculator, you might want to put brackets up top and up bottom. On the bottom especially, well, really everything especially, it's easy to mess up. An alternative to this is do it in steps. So do step 1 and then step 2 and then do the division as step 3 and then do the cos -1 or arc cos as step 4. Whatever you feel comfortable with typing in on your calculator. So we'll do an example of this. Here we're looking for angles here. So I'm going to call this C, which means 11 is my other C. Make sure we're matching that. So I'm going to copy the formula just how I see it above. Cosine C is equal to a squared plus, oh, I lied. I don't know why I put the b squared up there first. It is inconsequential. The only thing that matters is that C is the one we're subtracting, 2ab. Then I'm going to go ahead, I'm going to insert my values. So I've got 30 squared plus 35 squared minus 11 squared divided by 2 times 30 times 35. All right. So I'll go ahead and I'll do my top first. 30 squared plus 35 squared minus 11 squared. Then I'll divide by 2 times 30 times 35. And that gives me this, that cosine 30, or cosine C, sorry, is equal to 0.954 and some change. Remember, this value must be less than 1. So if this is not less than 1, it's not going to work. It's impossible. And so that's just an example of a triangle that couldn't exist as given. So made sure I didn't put any of those on my notes. So once I want to find actually angle C, what I do is use arc cosine. So that second function cosine of my answer. And that gives me an angle of 17.4 degrees. Does that answer make sense? Well, 17.4 degrees is a pretty small angle. And this side is pretty small. So, well, comparatively. So yeah, an angle that's pretty small kind of makes sense. Okay, so that's all fine and dandy. You've got some practice if you want to work on some more examples. That's the unit. So one of the things that we really didn't look at in this video, and is really kind of on your end anyways, is using applications of this. So taking like contextual problems. So if you're using this to kind of guide your studying, I highly recommend that you don't just do the basic examples. Also try and do word problems and contextual problems where you have to apply these to real life or pseudo real life situations in order to find missing values. Hopefully you found these videos helpful, and I will see you in class or in the next one or something. We'll find out.